Okay, let's get started. Welcome everybody to coding theory. CSS.318.1. So you know this is going to be a 4-credit course. It will be offered on Mondays and Wednesdays, 9:30 to 11. It's early for me. I think it's also early for you to get up. Didn't expect us to have to get up this early, but fine, we will live with it. It's the most convenient time in the course scheduling. So a couple of let me get through the administrative part of the response before we details. Firstly, even before that, so usually I have taught in-person classes where I use the board, or during the pandemic I moved to using the iPad and stuff and having notes. Students felt it was convenient to have these transcripts of the lecture notes available immediately after class, so that you don't have to take notes during class. You can this one. So this is the first time I'm going to do this. I'm going to actually be writing on the iPad during lecture. So I won't be using the board, I'll be writing on the iPad so that at the end of the lecture you have the transcript. We'll see this how it works for a couple of lectures. If it works out fine, we'll continue with this model, or I'll shift to the Blackboard. So that's one. So as you know, I'm Prahladh Harsha, and this one I think I've seen most of you. Everyone,
yeah, so I'm Atif.
You're Atif. You're Abhishek. Yeah. This one. There's one other first-year student in the class, Shantanu. This one he had registered in the list. Okay, so I participated in the welcomes meet, but I couldn't see any one of you. I think you guys saw me welcome meet. So I'll be the instructor for the course. Ashutosh Shankar will be the teaching assistant for the course. By now you would know the course has a web page. All information about the course will be posted there, including the links to the videos, the problem sets, and everything. I'll hopefully update this by the end of after each lecture. By the end of the day of the lecture, the web page will be updated with information regarding what happened in that lecture. Okay, so let's get on. So for those, how many of you are actually taking the course for credit? Okay.
For now, I've selected it
as credit. Okay. So the grading policy, how is it going to be? So let me There will be 4 problem sets. 4 problem sets. So they will, at the end of this week, I'll give you the first problem set. Each problem set will have 2 weeks. There'll be a 1-week gap. The other problem set, so it will go on like this for 12 weeks. 3 into 4, 12 weeks, you'll have problem sets. The way it will work is you will be graded on the best 3 of the 4 problem sets. So you can, depending on how your time spread your effort across, you'll be graded upon the best 3. Furthermore, problem sets have to be handed in time. But each one of you will be given 14 days lax time. You can spread this 14 days across the 4 problem sets however you want. That is, first problem set you can take 2 extra days. The second problem set you can take 3 extra days. Spread the 14 days however you want, but no more than 14 days. If anything crosses above 14, that problem sets I will not count into this one unless there are valid reasons for you, and the problem sets will contribute to 80% of the grade. And then there will be a final, there will either be a project, this will actually be your choice. There will be a project with a presentation or a paper presentation. Or a final exam. I typically don't like to have final exams in class exams for advanced topics like this. I prefer problem sets and presentations, but those who are taking the course for qualifiers, we need to have a final exam. So those who are planning to take the course for qualifiers will have to take the final exam option. There's no other one. The others, you are free to choose among the 3. I would prefer you choose the first 2 rather than the final exam. And that will be 20% of the grade. Okay. Yeah, so we need to have a final exam for courses which have for which we're going to have a which are included for the qualifiers, so that you get to know what sort of exams problems come on the qualifiers. And what else do I have? That's it. Is there anything else? Yeah. This week. So already I'm possibly the last course to begin. Most other courses have begun. I'm already behind schedule, and Wednesday happens to be a holiday due to Vinayak Chaturthi. So I want to know if I could have a makeup lecture on Friday instead. So it will be in the morning. So I'm assuming there is no system science student taking this course. System science first year student taking those courses. Fridays, the 2 morning slots are MFCS and MFSS. The 2 morning slots, 9:30 to 11 and 11:30 to 1. So I'll choose one of those 2 slots. I'll send an email across the grid. So the first class will have a makeup lecture instead of Wednesday on Friday. Otherwise, we'll stick to the Monday-Wednesday schedule, because I would like to have 26 lectures, and we don't have enough time to 26 lectures if I don't need this. Okay, so that's one. So let's get to the topic. Let's get to coding theory. So what is this course about? What are we planning to do in this course? The coding theory is basically the study of this object called error correcting codes. So these error correcting codes, which were introduced by co-invented by Shannon in this celebrated paper from 1948, where in the same paper he also introduced information theory, and by Hamming a couple of years later. 50. And they had their motivations for it. They had sort of models, and they have motivation for introducing this. We will come to the Shannon model, the Hamming model shortly. But what I will do in today's class is I will not define what codes are, what this one. We will take 4 sample problems that happen, possibly games, real life scenarios, talk about 4 problems and see why codes will enter the picture. We won't solve these problems, but I'll mention each of these problem instances, tell you what the problem is. Hopefully by the end of the course, you will see a solution to all the 4 problems. So hoping that these 4 test cases will sort of motivate you what codes are and stuff. So we won't unless I do it well in advance, I won't even define what a code is till the end of the lecture, or possibly next lecture. We'll just look at 4 toy problems. Some of them might be very real life scenarios. So won't talk what Shannon is, Hamming did and all. We'll come to it. Hamming possibly we'll talk about it a little. By the way, I think there are students from both the computer science and the system science stream. Typically, I have been teaching this course from a computer science perspective, but that's how I taught it in the previous iteration of this course. I will change it a little bit to have more. So typically, the Hamming model is the CS view of coding theory. The Shannon model is the SS is the E view of coding theory. We will try to do a mix of both, though it will still, I'm biased towards the Hamming model. It will have a fair amount of Hamming. We'll see actually these models are extremely related to each other. So solution in one will imply solution in the other. We will talk about these models in detail, most probably in the next lecture or the 3rd lecture from now. But let's start off with some toy examples. First example, example 1. What I've seen this is guessing hat speed. So what is the problem here? So say there are 63 of you. See why I talk about the number 63 later on. There are 63 of you, and each of you, I put a red or a blue hat on your head, and I pick it randomly, independently for each one of you. Each one put a red or blue hat. You get to see the hats of all your neighbors, everybody else in the room, but you don't get to see your own hat. So 63 of you, you can't communicate amongst yourself. I put a random hat, random colored hat, either a red hat or a blue hat on each of your heads. And the goal is you need to decide, each one of you needs to decide determine the color of your hat. So you get to either say what you think is the color of your hat or you say pass. And the whole class, you need to come up with a strategy for the entire class such that once I do this sort of thing, of course, the one way of winning, one way of saying is everybody says pass. So, the class wins. There's no such thing as an individual wins. The class wins if at least one person does not say, if at least one person does not say pass, and everybody who does not say pass gets it correct. So you can't all be saying pass. So you follow the question. So by the way, feel free to stop and ask me questions. This class is best if it's interactive. You follow the question. I put here 63 of you. It could be 15 of you, or it could be 7 of you, and now you know why I'm talking about 7, 15, 63, or 31 of you. I put random hats, red and blue on your heads. You don't get to see the hat of your own color, the hat on your head. You don't get to see the color of the hat, but you get to see the color of the hats of everybody else, all the remaining 62 people in the classroom. You need to, based on that, determine what is the color of your hat. So if you can make a guess.
One person doesn't know that how many divisions are there, because the odd number, right? How many blue and red hats are there?
Huh?
So 63, I suppose.
Yes.
63 hats.
Yes.
But I can see every other's hats colors.
Yes.
Still the probability you have for me that.
Yeah. So watch the thing. So you need to come up with a strategy. The class wins if at least one person does not say pass, and every person who doesn't say pass gets determines the right color. Now, clearly, with probability half, you can win it. The probability is over the random choices of the hats. So you could decide that only the first person, only Ashutosh will answer, everybody else will say pass, and Ashutosh always says red. So half the time the class is going to get it correct. But that's only half. My question is, can you do better than half? Is there a strategy for you to do better than half? By the way, this problem did appear in the New York Times several years ago.
So, you ask each person one at a time.
No, they don't get to know the answers of the people.
Yes, everyone has to answer at the same time.
Everyone has to answer at the same time. Yeah.
The persons are distinguishable with level.
What?
So the persons are distinguishable.
The persons are distinguishable. So yeah. So you're all indexed 1 to 63. Yeah. You have your names and IDs. What do you think can be the probability of success? Can you do anything better than half? What do you think? Yes, if you might not have a strategy, it's not easy to come. If you do not know this problem, it's very hard to come up with a strategy. By the way, this would be your first problem in your first problem set. So it's not easy. Yeah. But what do you think?
Use pass as a code so that you communicate. Somebody says, so there is some person A and there is some other person B fixed. And if A says pass, it means that so they can see.
But they don't get to.
Yeah.
You can't answer based on another person's answer. You all answer simultaneously.
Okay.
You all answer simultaneously. So you cannot be messaging via your answers.
And the answers are either red,
Blue, or pass.
They are the subset of the number of possible subset of the possible assignments, which density more than half. That's it. For every element in that subset, at least one element is determined.
Yes. Yeah. And strangely, that you can make the probability 63 over 64. 63 over 64. We'll see how to do this. It's going to be. Yeah. So I want to. Yeah.
I didn't hear what he said.
No, he was just giving, what he was trying to say was just an equivalent interpretation of the whole problem. If you say it in mathematical terms, it's the same the thing. So that's the question. I just put in hats in this one and all into make it more fun. That's the question. Yeah. Okay. So surprisingly, you can do it with probability much better than half. Think of the probability. If you lose out in the class, think of it if you can do anything better than half. And strangely, you can do very, very close to 1. Seems stunning, seems shocking. Yeah, but you can do very close to 1. But let's go to example 2. And strangely, the solution to example 2 will actually be related, will determine the solution to example 1, and you will see why that's the case in the problem set. Neha, you had a question?
They're allowed to be wrong.
Yeah, they're allowed to be wrong. So the question is, what's the probability that the class wins? So there are certain times the class loses, certain configuration. So you could certain configurations for which so happens you lose.
So if only one person says, if there's like at least one person who says blue, but if she's wearing say red, then class loses, right?
The class loses. Yes. If even if so, the class loses if everybody says pass, or if there's one person who says pass but determines guesses wrongly. Then there is. And you want to maximize the probability of the class win.
So everyone to win on a subset is subset of 0, 1 power 10.
Yes.
And if it is true that every element of S is in a coordinate boundary of S, then this can be done.
Yeah, this can be done. Yeah, question is what is.
So we want the large subset S such that every element of S is in a coordinate boundary of S.
Fair enough. Yeah.
Some isomorphism.
It will be some experimentary thing. We will see why it is. I won't explain it. It will be by the end of hopefully today's lecture, or the beginning of next lecture, you will see why what we are talking will actually answer the problem. And in the first problem in the problem set 1, we'll actually I'll break this up into parts, and you'll may basically prove whatever.
How do probabilities come in here? Like
the probability is over the random choice of this one. So it's 2 power 6. The number of possible configurations is 2 power 63.
So if a first person always says blue, then the probability is 1/2.
The probability is 1/2. If the first person says blue, so you guys can talk amongst yourself before I put the hats to decide what way you're going to say pass red. Okay. Let's go to example 2. Example 2, this is sort of what is called Hamming. This was a problem which Hamming was motivated by. In some sense, it's a motivating example for one. And it's the thing, you want to store data on a device, say a magnetic strip, your hard disk or something, and the storage device, or you're transmitting, or you're talking over a telephone or something. The data is being written somewhere, and these mediums of storage are not necessarily perfect. The corruptions do happen once in a while, but corruptions happen very rarely.
So,
Yes.
in the first problem,
Yeah.
so you said that everybody can, one person can see any other hats.
Yes.
Right.
Yeah.
So if we begin of the problem, before the putting the hats,
Mhm.
we mark everyone according to order 1, 2, 3, 4, 5, 6 to 63.
Mhm.
And we make 2 boxes, like 2 barricades.
Mhm.
When they decide to do barricades, one of same red color or blue color.
Yeah.
So after putting the hats,
Mhm.
the second person will see the first one and decide if it's red, he will go to the one which marks in the blue barricade.
Yeah.
And so on, decide on the 2, so he will choose to go who's next barricade, and so on.
Okay.
And then the first person will go to the other barricade
Okay.
and continue towards the 63.
So in some sense, what you are trying to say is we'll assume that if you put it in this one, we'll assume that the parity of the hats, let's think of the hats as 0, 1.
Yes.
In some sense, your solution will be equal into the following. I believe it is that we'll assume the parity of the hats is always even. We will answer in this setting. That's what sort of happening. We'll assume the parity of the hats is even. So the last person will be able to guess their hat if you know, if you look at everybody else's based on it, but this will still give you only probability half, if I'm right. This will still give you only probability half, because you will be answering correctly for the even strings, for all the odd strings, you'll get it wrong. So you have to do a little more. I think this is what your solution translates to. And I think, because basically you're drawing this cycle of, you're drawing this long cycle of 63, and each one is determining the next, and finally you're completing the cycle. So basically, you're going to sum up all the guys' hats and say whether if it's even, you'll assume that the thing is even, and the last guy will answer accordingly. Otherwise, you can assume you either get correctly only on even strings or only on odd strings, but this will still give you only half success. Okay. Think about it. Okay, so let's go to the next example, which is Hamming's problem. Hamming's problem is one. So you're going to store n bits. Store n bits, say on some magnetic strip or something. I'm going to store them. And corruptions happen occasionally. Happen, but rarely. And somebody promises to you that no more than t corruptions happen. Well, they say that corruptions do happen. Most of the times it always works fine. Every now and then a few things, and think of t as number. Say one way of modeling this is at most t corruptions happen. And we think of t as some number significantly smaller than 10. Now, is there a way of writing? So certainly now you can't, all the n bits, all the n things, symbols can't be completely distinct symbols. You have to add some redundancy, because if they're completely distinct, you will lose the t thing, corruptions. Question is, how do I write things on this so that I can handle t corruptions? I want to write n symbols. So think of the symbols as bits for now, n bits. This is the amount of storage I have, but the storage device is slightly faulty. That is, it doesn't necessarily store it perfectly. At most, t corruptions can happen. Now, despite the t corruptions, when you look at the n bits, you must be able to recover what you wrote originally. So certainly one way of writing is I can certainly store 0 or 1. So I can just write 0 n times or 1 n times. So certainly I can. And then you basically, depending on the corruptions, if there's, you'll see the majority and you'll be able to recover. So let's make the problem a little more. This one. Let's go back to our favorite number. Suppose n were 63. The 63, and the reason I'm 63 is this will actually solve the first problem. So there's an n. So you have a 63 long magnetic strip in which you can store 63 bits, and you are said that at most one corruption happens. Zero corruptions might happen. Now, how many distinct strings can you store on this so that even if one corruption happens, you will be able to recover it?
So corruption is
what's a corruption? Good point. What's a corruption? A corruption for now is going to be 0 can go to 1, 1 can go to 0.
And the index is not.
And you know which index is corrupted.
I know which index.
You know which index. So there are n locations in which you are storing the n bits, and corruption just means a flip of a bit.
I know which index is corrupted and I will split that index.
No, you do not know which index is corrupted. You don't know which index is corrupted. You say things have got corrupted, you don't know which index have got corrupted, but things don't get So there are ways. So now, of course, once you talk about corruption, the various corruption models we can talk of. The thing gets erased. One is the erasure model. It gets erased. 0 doesn't flip to 1, 1 but the thing gets erased. It gets smudged. That's one notion of corruption. Other is it gets erased, but the thing compresses. So you do not know which location has been erased. That is an n-bit string now becomes an n-1 bit string. It could be, so this is what I'll call a deletion rather than an erasure. Erasure is which, but right now I'm going to talk about bit flips. The corruption being 0 is flipping to a 1, 1 flipping to a 0. And we will look at all these models of corruption. Depending on the underlying medium, there will be different notions of corruption, and we would want to handle these corruptions. We'll come to all of this detail. For now, for this specific case, today's example, let's take in which you have this long in long, it has a sequence of 0, 1, 0. That's what you write on it, and at most one corruption can happen. So say this 0 gets corrupted, and then the rest is all. So that's the corrupted location, but you don't know which is the corrupted location. But despite this corruption, you must be able to tell what you had written originally.
So correction happened exactly with probability 1 or not?
It might not happen at all. It might not happen. There is no randomness in this question. There's no randomness. There could be a corruption, but at most one corruption, or there may not be any corruption. Irrespective of that, looking at the receipt, this is what usually called the original message, the encoded message. This is the received word that is after the corruption happens. So there is some corruption happening over here. There's some corruption happening over here, and it gets corrupted, and you still want to be able to recover. That's the question. And what we want to know is I want to store as many bits as possible. I not only want, so there are two questions you can ask. One is I want to detect there's a corruption. Other is I want to actually recover the thing. The first is an easier problem. So suppose you just want to detect something, whether a corruption has taken place or not. Can you solve this problem?
Taking one corruption, like add one parity.
So add a parity bit. So basically the original message is only the first 62 bits, and then the last bit is just the parity of all the bits. You then look at this, and if I guarantee you that at most one corruption happens, you look at this, if the parity is even, you know that there has been no corruption, because this is because of the promise that I told you there can be at most one corruption. If there's more corruption, all bets are out. But so detection is an easier problem, but what I want to do is actually not detection, I actually want to recover the original. So there are two questions over here. Question regarding how to handle corruptions. One is just detection. And detection, this is easy in the sense that you can store, essentially you can store n-1 lists. They basically, in other words, I can store 2 power n-1 possible strings. And the last is just a parity bit with parity bit. And we'll be able to detect if there's a corruption. The other question is actually I want to do recovery. I just don't want to tell whether there's been a corruption. Notice the first one will not tell you how to fix the thing. It will tell you there's been an error, and then you have to do something else to do it. Sometimes just detection will be sufficient for our applications, but there will be places where actually you will also want to be able to recover. Most cases you would want to recover. Question is, what do you do for recovery?
If we measure the strings that we store, so it takes at least 3 bits to get from any one code word
to another code word. Yeah, then we will be able to. This is exactly what we will come to. This is Hamming's solution to this particular problem. For n equals for n and t equals 1, a 3-bit flip. As long as the set of code, what we'll call the set of code words, are always 3 bits apart. Any two distinct ways are 3 bits apart. You'll be able to handle this, and you'll see why it comes to later on. So keep this problem in mind. We'll come back to this later on, but I want to go to actually example 2a, which is a very closely related example. By the way, so this is not this is a very useful example because such corruptions do happen all the time. Hard disks do fail and stuff. In fact, they are not perfect, and we always encode them. Use some code to write things so that even though, so when the readers are reading it, they are going to be automatically doing these. First, they will do a detection, and then they'll be doing a recovery. So this happens almost all the time. This happens when you write things on the disk. This happens when you're speaking across on a telephone. This is how your voice gets encoded. There's enough redundancy added. Everything, there's an encoding process, there's a decoding process. that happens. 2A, we'll take a more involved example of this, of how data centers handle. So this is just how data centers handle storing applications. So you have something like Facebook or the Microsoft Messenger, which has data stored. They have all your data, but these are not stored in a single location. It's not one magnetic strip. They are stored across the world in different data centers. So one sort of simplification is there's the actual data is say n bits long. N is huge, it's trillions and trillions of bytes, bits of information, and you're sort of splitting each of this is a data center. Each data, so there are m data centers, each of it with say p bits. So n is mp. That's the total number of response. And now this is how your data is being stored across. You want to handle errors in this setting. What sort of errors you want to handle? So because these data centers are split, this one, sometimes you want, there are two types of errors. Unlike previously, the corruption, let's talk about the same corruption model, bits are getting flipped from 0 to 1. There are things you still want to guarantee against some sort of notion of corruptions. Previously, we just had a global bound on the number of corruptions. That is, we were going to guarantee that we can recover against key corruptions. That was the model I talked about. Here, we will want to distinguish between both local corruptions and global corruptions. That is, because a local corruption, a data center can handle it itself. Every now and then it will check, find out if there are corruptions and be able to fix it. The global corruptions, you have to check if the data is consistent across data centers, and these are usually more expensive. So you'll have two notions of corruptions. You want ways to store it such that you have, say, just at most L local errors, local corruptions, and at most G global corruptions. And typically L is much larger than G.
So what's the definition of a global?
Global is the G bits are corrupted, but a corruption happens, but a corruption is happening across. That is, corruption happens due to some erroneous writing or some failure or something. So it could be a local failure, it could be a global failure. So it could be just a locally each data center wants to maintain the consistency of its data. Then globally, the data centers also keep talking with each other to ensure the data is consistent across each other. And you want some guarantees on how data is consistent. So typically how they will model it is they'll say, whenever, as long we'll assume that there's a bound on the number of local corruptions that happen. And similarly, there's a bound on the number of global corruptions. So locally, say I can handle almost L corruptions. Globally, I can handle G corruptions. Can I come up with schemes which will upward this? Typically, L will be larger than G.
So if local corruptions are taken care of,
yeah,
then globally won't things be quite not failure?
No. So a failure could be a local failure, a failure could be a global failure. A single failure could be happening because things across multiple centers are getting corrupted. So think of it as the corruption has happened. Think of it as made up model, a cooked up model. But think of it as in a corruption. At every point of time, all the data centers check consistency of their data and check consistency across the data. They are going to check locally if something's one, and locally they can handle L errors, they fix it. But then they are going to talk with each other and find out if things. They might fix the errors locally, but then they realize globally it's not being consistent because some errors have happened across data centers. So then they need to be able to fix this also. So these are all questions. These are just, I'm just trying to say the question which Hamming considered was a very simple model which was sufficient. This one, today's sort of things we have to allow for the topography of the data centers, the topography, the way distributed. We'll have to take into account these more complicated ways in which data is stored, and we will have to come up with key coding mechanisms that handle this, and we will be doing this later. That's the reason why I'm doing. So typically one way of modeling it is we will talk about some notion of local corruption, some number of global corruptions, and try to come up with coding mechanisms that handle this.
So the formal definition of local corruption is simply a bit flip.
A bit flip.
And then what's the formal definition of?
Both are blit flips. The local definition is there are so, and what's an error? There are at most. So I want a way of writing things such that if there are at most L errors that happen within a data center, we should be able to fix it with that particular data center alone handling it. Or if there's at most G errors, but these G errors happen not at a single data center, but spread across. It could be like 2 over here, G minus 2 over here. Then they must be able to handle it. Then also we must be able to fix the errors. So there are two notions of errors we are talking. So global errors are more expensive to fix. Local errors are, because at every point of time, the data centers are constantly talking with each other to fix the error, to check consistency of data across data centers and within data centers. They want to do both of them. We'll assume globally there's a little more consistency always maintained this one. So we will try to come up with schemes to do this. I'll define it formally later on in the course, but depending on our applications which we are talking about, these models of will vary. That's all I want to impress upon at this point of time. So this is just a more sophisticated model than what Hamming had talked about. Okay. And each of these we will is what I call secret sharing. What is this? So there are n parties, the n people, and you want to share a secret, say a number, say a bit among the n parties. But you want the secret to have the following property. So want to share a secret. So these are the properties I want to share a secret. Among n people. You have to define what a secret is and all. Let's be a little informal here. Such that if any T of them get together, they should be able to recover the secret. There is no individual person can recover the secret themselves, but if T of them get together, they should be able to recover the secret. If T or more people should be able to recover using their shares. Recover secret. Using their shares. T minus 1 or less people, if they join together from their shares, they must not be able to find anything about the secret. So it's basically this sort of voting mechanism. If a certain number of people come, they are able to have the combination to the lock. If any person less than it come, they are not able to. These are called threshold secret sharing, and you can keep the threshold as arbitrary. This one right now it's T minus 1 versus T. T minus 1 less cannot recover. We have to formally define what cannot recover means. Cannot recover from recovered. So this is called the T minus 1 versus T secret sharing scheme. Have you guys seen this? You know how one implementation of this.
You can do something with polynomial. So like if you want, like, yeah, exactly. If you want that T or more people, like whatever is the secret, like let that be like the coefficient vector of like degree T or some degree.
So yeah, so what you're trying to say is the following. Suppose you want to share a field element. A field element is this. Let's work with some finite field. You want to share a field element. One way of doing this is pick a random degree T polynomial whose zero coefficient is this field secret share. The other coefficients, it's random otherwise. That is, all the degree 1 coefficient, degree 2 coefficient, all the way up to degree T coefficients are random. The zeroth coefficient is the secret you want to share. Now go to the n parties. So you have a polynomial. You have determined a polynomial based on the evaluation, based on the coefficient vector. coefficient, the 0th coefficient is the secret. The other 1 to t are the share are random. This determines the coefficient vector of the polynomial of a degree t polynomial. Now, suppose there are n people. I think of n as certainly larger than t. Take this polynomial and let's assume the people are 1, 2, 3 up to n. Evaluate this polynomial at the points 1, 2, 3 up to n and give it to them. Now, I claim if anything less than t people join together, they know nothing about the polynomial. In particular, they will not know anything about the 0 coefficient. But if if all t parties get together, they will be able to recover they will be able to interpolate to it. This is secret sharing using the Reed-Solomon code, but you will more generally see that any MDS code will actually satisfy these properties. We'll come to it later.
I mean, here when we said cannot recover, we wanted them to not be able to do better than just guessing.
Yeah. So I haven't defined what cannot mean. Cannot is you have to formally define what it means. That is based on the randomness of the scheme. They must not be able to tell the secret is this or that better than what a random guess is. So we have each of these have to make a formula, and we will do it if and when we come study these problems. So the last example which we will see before we go into more one is something that became very important in the last few years. So you want to, we have to test people to find out how many people are positive. Also, we have these testing schemes. So there's a pandemic going on. You want to test people to find out who's positive and who's negative. But we don't have as many tests as the number of people. The number of tests is much smaller than the number of people. So but yet you would like to test people. And in the general population, it's okay to make false things because people don't interact with each other. But suppose you're testing health workers. This is a group of people whom you really want to know who is positive and who is negative. Because a positive health worker, they should be sort of quarantined from the rest. They have a bigger possibility of spreading the disease. So I'm just going to give data from one of the experiments that happened early on in the pandemic.
It's like making, suppose the saliva test to
Yeah.
So there are 8 people.
Yes.
Suppose 8 is even.
Yeah.
So there are 2 firstly, and there are lesser number of tests, right?
Yes.
So the one who are taking the test will say that half of them will split in a single box, another one in a byte with another box. So among those, they will check is there a positive case or negative case.
How will they check?
With the test that will.
But how many tests will you do?
And reduction by that, right?
Yeah. So what you're suggesting is the following. Take the number of so let me tell you the test cases happen and then come to your solution. So early on the test cases, there were n equals 384 health. This was actually 384 health workers. Each of them gave a saliva sample. Saliva sample. You had to collect samples from all of them, but you're not going to necessarily run 384 tests. What happened? The experiment ran only 48 tests. 48 tests, and it correctly detected the 4 positive people among the 384. So this was done. So one suggestion is the following: that is, take the 384 people, split them into 2 halves, combine all their salivas, do 1 test for them, 1 test for them. If either of the tests, I'm assuming that the test will turn positive even if one of the guys is positive. Do a positive test. Now, if any one of them do it, go further. There's one problem. This will work. So it goes. There's a logarithmically many rounds. The one issue with this is the fact that this test is adaptive. That is, I have to keep on getting samples from people. And it's also sequential. That is like the test, I have to wait for one test to be over to do the sort of next test. We don't have some test take typically 9 hours and this one. I can't sometimes do these sort of things. So in some cases, this might be okay. It might be okay to do this in sequence one after another. In other instances, this might not be the case. For example, in the pandemic, at least we could not do this in sequence. We had to do these in parallel.
So you want one time.
A one-time way. So actually, in this particular thing, they took 384 things. They somehow combined. So they took the 384 samples and they mixed the samples in such a way and made it into 48 sample buckets. And based on the 48 buckets, they were able to exactly find out who are the 4. They done just 48 tests in parallel.
So what are the options?
So what are the options? So certainly, by the way, this is not doable if it's possible that everyone can test positive or negative. Certainly, if you can do that, then there are 2 to the 384 possible positives and negatives. You need 384 tests to actually detect which particular situation. So once again, like in Hamming's question, we'll assume that there are no more than say 10 positive people in the model. We'll assume something about this one. Given that, now that I tell you that the number of positive people is somewhere between 0 and 10, I do not know what this is. This is exactly the same scenario as Hamming. This one. Now can you design a testing mechanism so that you can find out who are these at most 10 people who are tested, who are positive in this.
NCK. You can make.
You are doing
NCK subsets and
yeah.
As k goes to mid or middle, the number of sets will be lesser and lesser. And you can
Well, the number of
NCK, but k equals to mod n by 2 box n by 2.
Yeah.
The number of sets will be more than we have, right?
No. So I'm assuming k is a small number. K is not like. So K is the number of positive people. What fraction of this one? We typically assume there's a 1% for this one. You are setting as n by 2, in which 50% of this one. In that way, it's n choose n by 2, which is almost 2 power n. It's 1 over square root, and you would need to basically run all 384 tests in that case. So I'm assuming there are only like say 10 positive or 5 positive people in this, and I want to do how to do it. And this will also be actually coding is what comes into this. And we will see a way to answer this.
So what do you want to minimize the
number of tests? No. Everybody gives their samples. Everybody has to give samples, because if somebody doesn't give their sample, how will you ever? Everybody gives their samples. What you want to minimize is the number of tests that you need to conduct to uniquely find out who are all the positive people. Under the assumption that there are at most say T positive people in the population. If there are more than T positive people, you won't be able. You want it a little more than, you want the thing to be a little more than this. If there's less than T positive, this one, it should uniquely identify that. If there are more, it should, one way say the test gives runner. If there are more, it should at the very least tell you there are more. I don't know who they are, but there are more. You want it to say. So you say, then I do more number of tests. So you want, this is what you want on the testing. This one, if there are less than T positive people, you uniquely identify who are the T positive people. If there are more than T, the outcome of the test tells you that there are more than T, but possibly doesn't identify the more than T. This is what you want of the test. You can, that depends on this one. This is one. Their thing did not. This one, what they did, and what we will see actually at the end of this course, we will actually do pool testing. We will not be. We will see a thing in which it will not, if it's more than T, it will not detect it. It will detect it, but it will not identify the positive people. Less than T, it will identify exactly who are the positive people.
So here, like every person's sample can participate in different batch of tests.
So you're assuming you take a huge swab and yeah, you can participate in, yeah. There are these issues that come, but there are multiple issues. There will be simplifications which we do. That is, how much sample do you get from each person? And if you mix too many people's samples, if you put all 384 like samples together and test it, and if there's only one positive, is the test still sensitive enough to detect that one positive thing? There are these issues that comes, people do actually the tests that were designed. There's a group in IIT Bombay which actively did testing. Manoj Gopalkrishnan was part of this, actually came up with these things. They even consider these sort of things in which the sensitivity of the test can only detect if, as long as there's, say, one only if the percentage of positive should be at least so much when you combine it together. Okay. And so we will, so when you come to this specific question model, we have to define exactly what we're going to do. And the whole thing will be, first there will be an interesting question of how to exactly define the problem, and then we'll see how coding will enter in and solve the problem. Huh? This example is a true story. This example is a true story. Huh? I don't know. I don't think this was this. No, these numbers are not Bombay. These numbers are not Bombay. I do not know how effectively they used pool testing within India. So IIT Bombay was doing pool testing as this one. Among its this one, they had a company also called Tessellation or something which the IIT Bombay. But I do not know at a national level or even at a state level whether India ever implemented pool testing.
At some point, the positive rate was lower, right? So
No, but it still was, yeah, the positive rate low. Israel was using pool testing initially. So after it processed 10% and all, I don't think it's, so n choose Kn is pretty large. You basically have to do at least log of n choose k, where k is the number of, that's not, you can easily show this, you will show this when you go to this, log of n choose k you have to do. So if k is like a constant, k is like 10 to 0.1 n, this is already a large number, then you might as well test this. You don't have to do these clever mixing and put lists. Okay.
I think Suhail has some interesting video.
Suhail has a video on this. Suhail has a video. Okay, so those are the 4 examples I wanted to say. These examples will actually, each of these cases, we will formally define what the problem is. We will give a mathematical definition of the problem and show how codes can come to our rescue and solve each of these problems. By the end of the course, we'll see this and several other scenarios. But to begin with, let's go back to Hamming's problem and try to come up with a solution for it. What am I doing? No, we'll try to do some part of the solution, and the rest of it we'll do the next lecture. So once again, what's the question? So you have n equals 63. You can store 63 bits. So I'm going to always write these. Whenever I write a string of length n, I'm going to write it as a column vector. It will be more convenient for me because I'm going to view these as vectors eventually. And it will be easier for me to view them as column vectors rather than row vectors. So typically in e-books, many times I write this as rows. The string is written this way, but I'll find it convenient to do it because I like to do. So eventually we'll be doing a lot of linear algebra on this. I like to multiply vectors with matrices on the left. Other, if you want to multiply it on the right, then you write row vectors rather than column vectors. One, I would prefer this notation. So you can store 63 bits. So that's bits. At most one corruption happens. And let's take this special case, t equals 1, at most one corruption. What is a corruption? As Peter pointed, a corruption is 0 going to 1, 1 going to 0. That's a corruption, but you don't know location of corruption. Okay, so that's the thing. So we'll actually try the rest of this lecture and the beginning of next lecture. We'll actually try to solve this problem completely. The question, what I want to ask is, so I've given you a storage device which can store 63 bits, and I tell you the device is more or less corruption free. It can have at most one corruption or possibly no corruptions. Now you write whatever on it you want. Question is, and you want to read it so that when you read it, you are able to recover exactly what you have written. Question is, what is the maximum number of strings that you can, messages that you can store on this device? That's the question I want to ask. Question is clear? The question I want to ask, what is the maximum number of strings that can be stored on this device such that it can be recovered with getting, you can recover it, means you can get rid of the corruption when you recover it. By the way, so this process itself has two processes involved in it. One is you have a particular message, you're going to store it somewhere. That is, you have a message, you don't write the message in its raw format, you add some redundancy to the message and write it. This process is called usually the encoding process. And then there's another process in which recovery. So there are two processes over here. There's this involves an encoding process. This involves, you have something written there, from that you get back, you take out the corruptions and you get back your original message. This is usually called the decoding procedure. And a large part of the course will actually, you won't just come up with codes which just answer this question, in which these corresponding processes are actually efficient processes. Encoding, decoding, that's where the computer science part of it will come, but that will come to it later. So inbuilt into this question is also the fact that how fast is this and this process. Right now, I don't care, as long as there is some process for which you can store and some process which you can recover, to answer this question. Is the question clear? So let's come up with various candidate solutions. What's a solution? What's one way in which? So certainly, if you have just two messages, you can recover it because you just give the all zero string or the all one string and you can recover it. But already this should tell you you can do much better than this. What's one way of, what's a knife? What are various ways you can? I want to recover, not just detect. Yeah.
Like you store each bit in 3 bits. Right?
Yeah, so that's the first, this one exactly by the majority thing, but given that you only one corruption happens, so let's start with solution 1. Solution 1 is you sort of use majority, sort of repeat each bit 3 times. In other words, you have message, the original message is say 21 bits long. And you take each bit and expand it to 3 bits. And you just repeat it. So if it were a 0, it becomes a 0, 0, 0. If it were a 1, it becomes a 1, 1, 1. So you have a 21 initial bits. Then you expand it to 63 bits. Why can you recover?
From each of the element which appears at least twice.
At least twice. You know that there's at most one corruption. So in each chunk, at most there will be at least 2 things of the same number. You just do a math for each chunk. So there are 6. So you have 63 things over here. You break it up into 21 parts, and you do sort of majority decoding in each part. So there are some good things about this. What's a good thing? Firstly, both the encoding and the decoding process are extremely simple. Encoding is just repeat each thing 3 times. That's an extremely simple process. Decoding is this sort of majority. You take 3 bits, find out the most frequent bit among them, which one appears to at least 2 times. So both are very simple processes. And what are you storing? You are storing 21 message bits in 63 possibly corrupted bits. The actual thing, so this is what is usually called the rate. The rate, we define this formally, is basically the message length by the block length. Block length is n over here. So here it is 21 by 63, 1/3. So 2/3 is a redundancy in this. So the rate of this is this. So what we will want to ask is question B, can one do better than?
To arrange this 63 bits in a square with one corner knocked off. So it's an 8 by 8 square, one of the corners is 1.
Yes.
Then you interpret the smaller square, which is 7 by 7. That is the message block.
No, which, so it's an 8 by 8, yeah.
Yes. It's an 8 by 8, but one of the corners is not.
Yes,
So it's like a 7 by 7 with 2 rectangles, is it?
yes,
So the 7 by 7 is the message block.
yeah,
And then for the rectangles on the top row and this one, each of the top row bits is a parity of the column.
yes.
And each of the right hand column is the parity of the row.
The parity of the row. So therefore, good, you have, so it's a 49 things and you have added for 64 minus 49. So 14 extra redundancy bits. Yeah, so why does this recover against, how do you,
So if one of the message bits gets split, then you will see one column and one row with parity not adding up, so that will identify that.
fair enough, good. So this one, yeah, so this will certainly, the solution 2, this will certainly give you, the solution 2 is the following. Solution 2 is view was 8 by 8 square minus the corner square. This sort of object.
Yeah.
Everything except this guy. And the actual message, so this is 7, this is 1, 7, 1. The
We
actual,
also have that corner bit actually that will help with decoding.
no, the corner bit is, for his process, corner bit is not
No,
required.
because even those things can be corrupted, right? Even the,
If the column is corrected, you will only see one pair.
Only one is get, that thing doesn't add any further. So all you know is one of them is corrupted. You know something somewhere one is corrupted.
yeah.
Huh? If one of these is corrupted,
Then original message is not correct.
huh? Then original message is not corrupted. So you will, so you check each column, find out to which is a column corrupted. That will tell you is a column corrupted or not. Now check the rows. If both the column and a row are corrupted, you know the original message was corrupted. If only a column or row were corrupted, you know only the parity bits were corrupted, and you don't have to do anything. The message bits were as before.
And when only these, like the parity, if one of the parity things is corrupted,
Only a column will detect it, or a row will detect it. Both will not detect it. So this handles the thing here. Yeah. So certainly, so the message is going to be stored in the 7x7. So what's the rate of this?
49 to 60.
49 by 60. Fair enough. Okay. So what we will see is, so this is certainly significantly better than, the rate is significantly better than 1/3. The redundancy is only 14 bits, not 42 bits, as was in the previous case. So redundancy is very less, and still you can recover from one error. You can detect the error and do it. Hamming solution, and Hamming is just much better than this. Hamming will be able to get rate 57/63. That is, he's able to store even more number of bits, not just 49, 57, and Hamming doesn't stop at that. He shows you cannot do better than 57. 57. If you want to be able to recover against one error, 57 over 63 is the best you can do, and he will actually achieve this. Okay, so 49 is great. We will now see a scheme which will go up to 57. So this is better than before. Question once again is, and once again, this has a nice feature that encoding and decoding are extremely simple. Question is, can one even do better? That's it. So I'll actually, Hamming solution will take me a while to present. So what I will start off is I'll start with a smaller problem and make the 63 into 7, solve it for 7. Then we'll show how we can extend the 7 solution in 2 different ways to 63. One will not get you 57, the other one will get you 53. So let's, for starters, scale the problem down. Scale down n equals 63, n equals 7, but we still keep p equals 2. So I'm going to just pick this up out of the box, show what Hamming does, then we'll say why this is. What does Hamming say? Hamming is going to say, I'm going to look at, he says, consider this matrix G. It's going to be a 4 by 7 matrix. And the matrix is basically going to be this way. It's going to have identity as the first. And then the next 3 rows are going to be 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1. Okay. Is the matrix clear to you? We're going to take this matrix G, and what he will do is he'll take a message M, which is a symbol in 0, 1, 4. So it's M1, M2, M3, M4. We encode it by G. So encode it. So it takes a 4-bit thing and it's going to output. This one will be in 7. Okay. But in addition to this, Hamming also looks at the fall. He comes up with 2 magical matrices. We'll see why these are not really magical matrices. We'll see what the explanation for them. But right now, I'll just pull it out of the hat. See, this is 7, and then he comes up with another matrix, which is a 7 by 3 matrix. What is this matrix? This matrix is basically going to be the following matrix 0, 0, 1. Tell me if you see a pattern in what I'm writing over here.
All the binary strings.
All the binary strings, all the non-zero binary strings. It comes up with these 2 matrices, G and H, parallel, and makes the following surprising observations. which is essentially we had made this equation. That is for the first one is for all M1 not equal to M2 014 G of M1 and G of M2. We are taking 2 4 things. They actually differ in at least 3 bits. This was our original. If we who had said you had said that if you at least differ in 3 bits, then you'll be able to record. This is exactly the property. So GM1 and GM2 differ in at least 3 locations. So this is something which we will do shortly. If not in this lecture, we will. So this is exactly what Hamming had in mind. He came up with the G such that it has this feature. But furthermore, he also wanted to come up with an efficient way of identifying. This will tell you a way of identifying. Once you have this G, you can identify it by this one. But Hamming will actually give a more efficient way of identifying. What he observes is the H matrix is going to come this one. He notices that if you look at, let C be any string. Let's call it Y. Let Y be any string in 0, 1 to the 7. So this could be any 7-bit string, but let's assume it's actually got from the encoding of a message. Either it is the encoding of a message or an encoding of a message with at most 1 corruption. Suppose Y is GM for some MN 0, 1 to the 4 or GM plus EI. EI are the indicator vectors. EI for some MN 014 and IN 1 to 4. That's one of these. What Hamming observes is if you look at HY, so what is HY going to be? HY will be a how many bit string? 3-bit string. It could be all zeros, it could be a number between 1 and 7. What he shows is actually if it's all zeros, it will be the case, it says that there's been no corruption. Otherwise, that number, whichever is out there, is actually the index of the corrupted location. So it has HY is then HY is a 3-bit string, say B1, B2, B3, and magically B1, B2, B3 being all 0 string implies no errors. Otherwise, B1, B2, B3 else B1, B2, B3 is in fact the index of the corrupted. We will prove this. We'll prove this. Okay. So this will tell us how to do both recovery. Assuming these 2 properties, which I haven't yet proven, so I don't have time to prove this. I will not put this in this lecture. We prove it, or if you can, any one of you can either solve the hat puzzle or these things. We'll take it up in the beginning of next lecture.
So the hat puzzle will be, or let's say text, let's say it will be the complement of Hamming code.
It will be the complement. The Hamming code will play a big role in this one. Yeah.
So because everything that is not in the Hamming code lies in a 4-minute boundary of because every point we can.
Yes.
So
I haven't yet defined what the Hamming code is, but essentially yes.
Yeah.
Yeah, take a code with Hamming
This code.
with distance 3 and you'll be able to get. Huh?
is this Discord
Yeah,
for 63?
okay. So what's the rate of this code? In other words, what's the rate of this code?
In minus
No, this code I'm talking about. 4 by 7 is the rate of this code. 4 by 7 is the rate of this code. One way of extending this is you could just repeat, you could just like the previous time we broke the message into chunks of 3 each and had the majority code in each one. You could now have broken the 63 bits into 7 each, and each of them put this message length of 4. So the rate will still remain 4 over 7. That's how much. That's basically 4 in 7 into 9. 4 into 9 is how much? 36, which is actually weaker than what you had suggested. So this one you could just repeat this whole process 9 times. That will give you it will maintain. So the rate of this code is 4 by 7. To extend to 63. So naively you could just repeat 9 times. Then that will give rate. That will still give you rate 4 by 7. That won't improve the rate at all. But certainly you can do better, which was Hamming's final solution. So solution 3, which is Hamming's solution, was he came up with constructed 2 matrices. G is going to be a long. It will take 57 bits converted to 63 bits. And H will be a matrix which is 63 long. And here it's only 6. So that's 6 locations. And it has the surprising properties, which is exactly. It has the following properties. Both of which we will prove. That is, it's similar to the properties. For one, for all M1 not equal to M2 in 0157, GM1 and GM2 differ greater than or equal to 3 locations. 2 for a Y which is obtained for a Y in 0.63 obtained by corrupting at most 1 bit. So we have given this guarantee. HY is the index of the corrupt. So we will prove this formally. If you can come up with a proof of it by next by Friday, do let me know. So yeah, that was Hamming solution. But more importantly, so the rate here is, what's the rate here? The rate here is 57 over 63. Yeah, so we have already 3. We come up with 4 schemes, each with doing better than the other. Question is, can you keep doing and continue this way? What Hamming actually, the more important theorem that Hamming proved is cannot do any better. And we formalize this, what he exactly means. That is, no any code which can recover from at most one corruption, you cannot have redundancy better than 57 or 60. That's the best rate you can have. You can't have rate larger than this. Sure, this code. Yes, so that's, I mean, we will prove these things in the next lecture. I wanted to sort of prove it, but what I just want to take one getaway from it and we'll stop. So what did Hamming do over here? What was I mean, firstly, sort of he constructed a code constructed a specific code which had certain properties. Two, then he showed some limitations. He wanted some properties. He showed limitations of any code that has this feature, that has some property. Three, he also came up with an efficient decoding algorithm. He could have stopped with G. He also came up with H. H actually gave you an extremely efficient decoding algorithm. Four, which I have pointed out, this actually directly relates to the hats problem. Why am I writing this manner? A large part of our course will also be split into these 4 parts. We will be looking at, we construct some properties that we want. We look at what are limitations, combinatorial limitations of such. So there will be some combinatorial limitations of these properties. What's the best we can have? And then we'll construct codes which have that property. So these two will typically be combinatorially. This will be the initial part of the course we'll do. Then we'll accompany these things with the algorithmic counterpart questions for these. We'll talk about this one. So we'll come up with, so this property will change over time. We will have various other properties. We'll come up with algorithmic questions with the property. And then we will take these codes and see if they are related to other objects of interest. In this case, it was supposed to be hats game, but we'll see they'll have other connections in computer science and elsewhere. So a large part, so we'll see various applications to mathematics and computer science. The course is going to be divided more or less in these 4 parts, and it will more or less follow this order, but it will be these will be interleaved. So our course will have these 4 components. By the way, Shannon was also motivated by very similar this one, except his model was the only thing. His model and emphasis was different, but it also had the same sort of underlying thing. We'll come to Shannon's. This was exactly what Hamming did in his paper and followed. Of course, the hat question doesn't appear in his paper, it directly follows out of what he did. But the first thing, everything that he did was there in this one here. He actually gives formally proves everything we have done. So we mentioned today, we will prove that in the next lecture, the beginning of next lecture, which will lead us to formally define what a code is. And we'll start off with the basic preliminary notion, beginning of next lecture. And this will also be, as I mentioned, sort of a broad outline of the rest of our course. We'll have this. We'll talk about various properties of codes that we want codes to have. Are there, given this property, are there limitations, combinatorial limitations? This is one. And can we construct codes with these properties? This will go hand in hand with each other. What we cannot do, what we can do. And then we'll ask the things that we can do, can we also do efficiently? We'll talk about algorithmic coding theory. And then we'll see how do all of these objects relate to elsewhere in non-Hamming Shannon questions. So they apply to other areas of computer science. So that will be the broad outline of the course. So let's stop. Okay, we'll meet on Friday. I'll send email to find out what's the best slot, either the 9:30 to 11 or the 11:30 to 1. Yeah.
So it seems like for any, like there's always going to be like bounds on